This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, the professor for this class, and we're at Lecture 40, which is our third lecture on the topic of lithography. And today we're going to be talking about imaging tools used in optical lithography. Our reading is Chapter 7 of our textbook by Campbell. We have used this diagram before to show the basic steps in a lithography process, with the wafers coming in, being coated with photoresist, baked, and then put onto an exposure tool or an imaging tool. This is the tool we're going to talk about today, where the patterns on a mask or a photomask are imaged or projected or printed somehow on the resist-coated wafer. And that's what we're going to talk about today. Historically, we began in the early days of the semiconductor industry by using contact printing. It's the simplest form of printing. It has a slight variation called proximity printing. We'll talk about both of those in a moment. In 1973, the very first projection printers were used in lithography, commercially produced by a company called PerkinElmer. These were full-field 1x scanners. In 1978, the very first step-and-repeat printers came about, and this ushered in an era of rapidly rising capabilities of our projection tools in terms of resolution and overlay performance. We started out with a G-line tool with an NA of 0.28. I'll talk about what those terms mean later. Some of that today, some of it in a future lecture. And then about every decade we've been lowering the wavelength. So we lowered it in the early 80s to an I-line wavelength, but by 1988 we introduced the first deep UV stepper with a wavelength of 248 nanometers, and by 1998 we were at wavelengths of 193 nanometers. Seeing this progression, 1978, 1988, 1998, you might ask what happened in 2008. Well, something did happen. It's called immersion lithography, but we're going to save that topic to a much later lecture towards the end of our section on lithography. Let's look a little bit at this evolution with a simple diagram. Contact printing, as the name implies, means I take my mask and I put it in direct contact with the photoresist coated wafer. Here the red represents our photoresist on top of a wafer, which might have whatever film stack on it that we need. And we have a photomask, which is a fused silica plate. We tend to say glass, but today it's fused silica. In some days past, it actually was plain old glass, with some absorber, some material that absorbs light, blocks the light. Today mostly chrome, but there were other materials used then and now. We put this mask in direct contact and we shine some light and we get a shadow print. That's contact printing. Proximity printing, we do almost the same thing, but we lift the mask a little bit up and get a shadow print. But with projection printing, we use a lens or a lens system to project an image of that mask onto the wafer. And that's how we do things today. But let's talk about the historical contact and proximity printing for a moment first. Contact printing has a couple of varieties, what we sometimes call soft contact printing. We simply push the wafer up in a mechanical contact with the mask. There's different ways of doing that, including shooting air up to push it moderately gently to make a contact. But because of variations in the topography of the wafer, of the mask itself, the non-flatness of these two pieces, you don't always get perfect contact. So one way to improve that contact is what we call hard contact, where we pull a vacuum between the mask and the wafer and suck it down. And that's provides for the best resolution. And the resolution is on the order of the wavelength of light that we use to expose. These systems are reasonably high resolution. Today we can do much better than the wavelength of light, maybe a quarter of the wavelength of light typically. But nonetheless, at the time especially, the resolution was really not the problem. And they're very inexpensive tools. The mechanics of making a good contact are not that hard to do. So it's a very popular technique except for one thing, and that is defects. As you can imagine, if you've been listening to all these lectures, we've talked about defects, and we understand that anything that touches the wafer can generate defects, and we're very concerned about the impact of defects on the yield of our devices. So we have to be very, very careful. This is especially true when defects are on the photomask. If you get a defect on the mask, that defect can reproduce every single wafer. And the more defects you get on the mask, the more die that are going to die, chips that are going to fail. So we have to be careful about that. And we, with our contact printing, have a defect generating process built in to how we do our lithography. Every time I slam the mask down into the wafer, I generate defects. I damage the mask. As a result, the mask can only be used for a certain number of prints. Then they become too defective when you throw them away. In other words, the cost of losing those die is more expensive than the cost of a new mask, so we throw the mask away and get a new one. Well, in the days when we were printing 25 micron features, the defect size that would kill our devices was on that same order, maybe 25 microns. So 5 micron defects and 2 micron defects, well, they didn't really hurt us because they were too small. But as we begin to push the feature size smaller and smaller and smaller, well, then the size of a defect that would kill our device also shrinks. And there's always a lot more small defects than big defects. As a result, instead of printing a few hundred wafers before we threw the mask away, we go to a smaller feature. Maybe you can only print 20 wafers, and then maybe only 10 wafers, and then maybe only a couple of wafers. And eventually, every single wafer is going to have enough defects to where it's a problem. In other words, defectivity is the true resolution limiter for contact printing, and as we drop below 10 microns in feature size, we became limited by these defects. The simple solution, and the solution the industry chose quickly, was something called proximity printing. Here, we keep the mask and the wafer separated by a small amount. We put some little mechanical device that stops the mask and the wafer with a gap, maybe 20 microns gap between them so that they don't touch. You need a gap that's at least 10 microns, but 20 microns is pretty typical because you have non-flatness of the wafer, non-flatness of the mask. Things get tilted and moving around a little bit, and you can't really get them quite perfect. So you need at least that kind of a gap to prevent any accidental touching. Well, that solves the defect problem. But there's a different problem. This gap limits the resolution. The shadow you get is better the closer you are to the mask. The further away you get from the mask, the worse this shadow becomes. The shadow resolution is proportional, approximately. This is a kind of a simple approximation, but it's approximately equal to the square root of the wavelength times the mask wafer gap. So what kind of resolution can we get if we had a 400 nanometer wavelength, 0.4 microns, and we had a 20 mask to wafer gap distance, G? Multiply them together, that's 16 microns squared, take the square root, that's about 4 microns. And sure enough, we used proximity printing in the industry as our resolution got smaller, down to about 4 micron feature sizes. But then we run out of resolution for proximity printing. So what do? We need something that's a higher resolution and still avoids the defects. The way we did that is with projection imaging, where we project an image of the mask onto the wafer. We're going to see that there's lots of ways to do this, but the first fundamental question or problem you have to solve with projection printing is the very, very simple reality that our wafers are too big to print all at once. I simply cannot build an optical system that has a large enough exposure field. The exposure field is the portion of the wafer that can be exposed at once. And when you have a large wafer, even in the days of 3-inch wafers, that is simply too big to be exposed at once. So we need a system to expose a portion of the wafer and then repeat those exposures till we cover the whole wafer. Here we have the advantage of the fact that what we're trying to print are many repetitions of the same thing. We're printing 100 die, or 1,000 die, or 50 die, or some number of chips that are all identical. How can we take advantage of that? Well, the first way that we were able to expose the whole wafer with the whole mask is through a 1x full wafer scanner. These are the Perkin-Elmer scanners that came out in 1973. And they work something like this. I make a mask. It's a 1x mask, meaning it's got the exact same pattern of chips on the mask as I'm going to print on the wafer at the same size. Then my exposure field is an arc-shaped slit. It's maybe 10 millimeters wide, and the full width of the wafer across along the slit. And then I scan the mask and the wafer simultaneously past the slit. We don't show the motion here, but you can imagine this mask and this wafer are fixed together mechanically, and they're both being pulled in this direction. So part of the wafer has been exposed, and then the rest of it has yet to be exposed until that slit of light passes that portion of the wafer. A 1x full field scanner. Very simple design, and it worked very, very well throughout the 70s. But it became a little bit limited in resolution for two reasons. One is the particular optical system for these 1x scanners, which we're not going to go into, but the other is the limitation of a 1x mask. A 1x mask means I have to build features at the same resolution that I want on the wafer on the mask. If I use reduction, say 5x or 10x or 4x reduction, then the feature sizes on the mask are 5 or 10 or 4 times bigger than they are on the wafer. 10x was the very first reduction steppers, so we had masks that were 10 times bigger. But that's okay, because again, I can have a wafer that's much smaller than the mask, but because I'm only printing a small portion of it at once, I can live with that. So here I show a mask that has, say, 4 chips. So this particular exposure field size was big enough to hold 4 different chips in one mask, and then I have an optical system that projects a reduced version of that mask onto the wafer. And I'll get those 4 chips printed at once in the exposure field. When I'm done, I will step the wafer without moving the mask this time. I'm not scanning, I'm stepping. I step the wafer to a new location, then I expose again. Step and expose, step and expose. So this is called a step and repeat camera, because I step and repeat, step and repeat. But we generally just call them steppers. So step and repeat cameras, we do have some 1x versions of them, but the most popular versions were reduction steppers. Well, we can combine both of these concepts of scanning and stepping in what's called a step and scan tool, and this is what is very popular today. So we have a slit. Now it's a rectangular shaped slit instead of an arc shaped slit. We have a slit, and it scans one field. So this would be one mask pattern. It could have 1 chip, or it could have 4 chips or 16 chips or some number of chips, whatever can fit in this field, and I scan across the field. So in blow up over on the right, on the left I see it in a full wafer pattern. So I have one field and I'm scanning the slit past it. Now actually the slit, it stays stationary, and the mask and the wafer scan simultaneously past that slit. Then when I'm done scanning this slit, I step the wafer and then scan that slit past a new spot on the wafer. Then I step and scan, and kind of a serpentine pattern back and forth until I cover an entire column, and then I'll come up and do the same thing on the next column, back and forth, back and forth. I step, then I scan, then I step, then I scan. This has some advantages. First of all, I can use reduction. I can make the mask 4x bigger, and that's the popular reduction ratio that's used in all tools today that use step and scan is 4x. The mask is 4 times bigger and therefore 4 times easier to make. I mean, that's a crude way of saying it, but basically it's easier to make a 4x mask than a 1x mask. And I get some advantages in terms of the performance and the speed that I can expose. My optical system, instead of having to expose this entire field at once, only exposes the slit, which is about 8 millimeters wide. So I can reduce the complexity of the optical system by using a slit instead of exposing the whole field. The field itself can be made large, especially in the scan direction. I'm only limited by how far I can move the stage and how big I can make the mask. So the field size is at a maximum 26 by 33 millimeters on these tools. Because I've made the slit width smaller, my optical system becomes a little bit easier to fabricate, a little bit smaller itself. I'm basically trading off the optical complexity of the lens that projects the image of the mask in this slit onto the wafer to the mechanical complexity of stepping and scanning the wafer in the mask. And this trade-off turns out to be about optimum, and as a result, all state-of-the-art tools use this step and scan approach today. Another thing I'd like to mention in our overview of imaging tools is the light source. We've had a progression of wavelengths going from larger to smaller in order to improve resolution. And the earliest tools used a mercury arc lamp. Both the 1x Perkin-Elmer scanners and the very early steppers used these mercury arc lamps. And mercury arc lamps take mercury, put an arc or a spark across 2 electrodes, vaporize the mercury, excite it. When the electrons in the excited state fall down, they emit light in very specific lines that are a function of the element mercury. And we've named these lines various letters, F line, the fine line over here, but then lithographically important lines are the G line, the H line, and the I line. They're just named alphabetically, G, H, I. The G line is at 436 nanometers, and the I line is at 365 nanometers. This kind of elemental lines showing up in a lamp is quite a bit different compared to a thermal source like a tungsten filament light bulb, something that we still have some around today, although soon these will be gone as well as we move to LED lighting. But in a tungsten filament light bulb, we have a kind of a continuum of wavelengths, not specific wavelengths. Well, that's not very desirable for a lithography tool because the lens that's going to image the mask onto the wafer is designed to work at a specific wavelength. And so we need most of our energy centered around a wavelength. And we worry about the bandwidth. So here I show something like a full width half max, kind of a bandwidth, but I could also define it as something called E95, the range of wavelengths that keeps 95% of the energy inside of it. This bandwidth is on the order of 5 to 10 nanometers for G-line and I-line mercury arc lamps. So we get most of our energy centered around a very narrow range. And that has big advantages from the design of the lens. We began with G-line at 436 nanometers in the late 70s and early 80s. By the mid to late 80s, around 1990 time frame, I-line became the most popular at 365 nanometers. But then to move to smaller wavelengths, we switched from using a mercury arc lamp to using an Excimer laser. Excimer means excited dimer, and it's molecules like krypton and fluorine that are combined as gases in a chamber that we excite with high energy. Now, krypton and fluorine don't generally form a molecule, krypton fluoride. In fact, we don't even call it a molecule, we call it an excited dimer. The two things come together, but only when we pump a whole bunch of energy into the system. And then when they fall apart, they release light. And that's how we get our lighting action, our lasing action. Krypton fluoride lasers produced 248 nanometer wavelength light, and that became popular in the late 90s and early 2000s as the wavelength of choice. Then we switched to argon fluoride wavelength. Argon fluoride has a wavelength of 193 nanometers, and this is still the state-of-the-art wavelength used in lithography imaging today. These lasers are quite big and intricate systems. They're pulsed, they're not continuous wattage CW lasers. They're pulsed 4 to 6 kilohertz repetition rates. Quite a bit of energy in each pulse, something like 10 to 15 millijoules in each pulse. But the bandwidth is exceptionally small. You saw that with the mercury arc lamps we had 5 or 10 nanometer bandwidths. Here the bandwidth is 0.35 picometers. So very, very small. And there's reasons why we want it to be really small, and so there's a lot of line narrowing technology built into these lasers as well. So we've seen a progression from G-line at 436 nanometers down to argon fluoride at 193 nanometers with some wavelengths in between used in production lithography tools. The question is, can we keep pushing this? The big effort today is extreme ultraviolet, or EUV wavelength of about 13.5 nanometers, still not in production. And we'll talk about EUV technology at the very end of our discussion about lithography. We've seen this picture before. Here's an example of two commercial lithography tools. ASML and Nikon are the two biggest suppliers of lithography tools, and you see that a beam is coming in over on the side. In fact, the Excimer Laser is probably down in the basement, and they have some tubes with mirrors, and they just shoot the laser up, going through an optical system until it finally illuminates the mask. Here's the lens, and the wafer sits on the stage. And these are step and scan systems, so they're stepping and scanning at the same time. They're 4x, which makes for some interesting scanning because now the mask has to scan 4 times faster than the wafer, exactly 4 times faster than the wafer, to keep those images in their proper positions. And as I said last time, you might note that this is a computer screen at eye level for a standing human being of average height, so you can get a feeling for how big these tools are from looking at that image. Well, that's our overview of imaging tools. We're going to talk about the science of imaging in the next few lectures and understand exactly how images are formed and what the limits of resolution are. But in the meantime, let's look at what we've learned so far. You should be able to quickly and easily answer these questions. If not, go back and review the material. What are the advantages and disadvantages of contact printing? What are the advantages and disadvantages of proximity printing? What are 3 ways of filling a wafer with exposed chip patterns during projection printing? What are the 2 most common mercury arc lamp wavelengths, and what are they called? And finally, what are the 2 common excimer laser types and wavelengths? That's this lecture. We'll begin a discussion of the optics going on in these imaging tools next time. Till then.